was it and all. So we already on live. So you can go on mute. So I'll be displaying the various. I'll be running up
Okay.
background music and all that.
No problem, because I'm not very often using Zoom. Let me just check here.
Hi, good morning, ladies and gentlemen. On behalf of NFE, National Federation of Engineers for Electrical Safety, I extend warm welcome to all of you who have joined us today. This significant webinar focused on CEA Regulation 2023 and its implication on fault loop impedance. It's a pleasure to see such a diverse and enthusiastic audience representing various sectors of the electrical industry has come together to explore this critical topic. The CEA regulations play a pivotal role in shaping the electrical landscape, ensuring safety, efficiency, and reliability of our electrical infrastructure. Today, our esteemed panel of experts and speakers are here to share their knowledge, expertise, and experience, which will undoubtedly prove invaluable as we navigate these regulatory changes together. I encourage all of you, whether you are an electrical engineer, a regulator, or a fire officers, or industrial professionals, or individuals with keen interest in electrical safety, to actively engage in today's discussions. Your questions, comments, and contributions are vital to creating a rich and meaningful dialogue. Before we begin, I would like to express our gratitude to our distinguished speakers for their participation and support. It is your commitment that makes events like these possible and impactful. Thank you, and let's make this webinar an enlightening and engaging experience for all of us. Today, we have speakers. Mr. Gopkumar don't need much of instruction, so he is single-handedly carrying out the mission in spreading the awareness on electrical safety. He is our president, and what I can say, every month he is undertaking either physical seminar or webinar. Most of the Saturdays we are there. So I wouldn't like to read his profile, but he's a Sachin Tendulkar of electrical industry. With me I have a distinguished speaker, Piotr Pawlik. He joined us today from Poland. He is a graduate in electronics at Warsaw University Technology, Poland. He collaborated on several new meter designs, such as the MPI 530 IT multifunctional meter and the PAT 805-806 IT portable appliances tester, and adjusting our products to the US market. Piotr is a specialist who willingly shares his knowledge and experiences. He conducts online training webinars on meters and basics of conducting measurements. He has over 10 years of experience in the Sonal Group, actively participated in the implementation of new products, an experienced specialist who consistently implemented the strategy of building export market both Europe and in the USA. He has collaborated on many training, marketing, and sales projects. In his spare time, Piotr loves to travel, which allows him to meet new people and places. He was in India for the last 2 weeks. He traveled in length and breadth of the country, and he was very much appreciating the effort NFE is taking to spread the awareness. Myself, I'm the host for the day. I'm from the fire background. I've been actively involved in various society. And before I welcome our president, I urge all our participant today to join NFE. It's made of all different people from electrical community. There are electrical contractors, electrical consultants, manufacturer professionals. So I would urge my friends here, my colleague Lakshmi will be on the chat box, she will be connecting you to the direct link. And also we are coming out with next series of half-day program with BAS. BAS come out with a new initiative to cover all the tier 2 cities. So we are going to the smaller cities of various various states. So we will be soon introducing the physical half-day program. I would urge all the manufacturers who are there today to participate as the sponsors. You can come and present your technology and product. So I would now welcome our president, Mr. Gopakumar, to take over from here. Over to you, sir.
Thank you very much, Mr. Dominic. Let me share the screen. I will just set the background of this particular program so that Mr. Peter can take it up further. So, as Mr. Dominic told, we request all the electrical engineers, not only electrical engineers, the engineers, those who are, or people, those who are having interest in electrical safety and electrical technology, we request you to join NFE. We are growing very fast. More than growth, we are imparting a lot of knowledge, spreading a lot of awareness and knowledge to the entire nation. So, today I will just explain a little bit about the background of this particular webinar. Last week, 2 weeks back, we had a program in Gurgaon where we met Mr. Peter, and then Mr. Peter agreed to make a presentation about fault loop impedance, also his experience in the other nations, so just to explain us how the other developed nations are going. So with respect to India, I'm sure all of you are aware that the CEA regulation, which is the measures relating to safety and electric supply regulations. But before that, one question, Mr. Dominic, you are seeing my full screen or the half screen?
It's a full screen, sir.
Full screen. Oh, thank you. So the CEA Regulation 2023 has made NEC and National Building Code, National Electrical Code of India and National Building Code of India both are made mandatory. So if you wanted to make a building, an electrical installation which is complying to the national rules of India, then you are supposed to comply to the NEC and NBC. So these are there in the Regulation 14. So then if we go to today's subject is mostly about automatic disconnection of supply. That means in case of any fault, how to disconnect the supply and what are the modern methods to disconnect the supply, or what are the modern testing instruments available for making efficient automatic disconnection or to ensure automatic disconnection of the supply. So, but please note that it is from the Regulation 43. The old Regulation 41, but the new regulation is number 43. So if we look at the whole subject, it's a part of the safety measure called as fault protective measure called as protective equipotential bonding and automatic disconnection of supply. The regulation 43 in the sub-regulation 5 has written very clearly that protective equipotential bonding, every building, irrespective of whether it is a house or a hospital or a hotel or an industry or whatever, this safety measure called as protective equipotential bonding is mandatory. It is made, you can read it. Every building shall have protective equipotential bonding by interconnecting exposed and extraneous conductive parts. So, as I said, the complete safety measure is protective equipotential bonding and automatic disconnection of supply. With respect to automatic disconnection of supply, here you can see Regulation 43, Sub-Regulation 11. It says earth fault loop impedance shall be tested to ensure automatic disconnection of the protective device. This Regulation 11 is talking about the supplier, that means the DISCOM, the electricity distribution company. They are supposed to measure the fault loop impedance at the point of commencement of supply, and they are supposed to keep a record of the result for certain time for the electrical inspector to verify. Similarly, if you look at the regulation 12, earth fault loop impedance of each circuit shall be limited to a value determined by the type. And basically, this is the regulation 12 is talking about testing of fault loop impedance for every circuit. That means the user, the house owner, should do this particular testing. Actually, once when these clauses were included in the regulation, or more emphasis was given to this particular clause or fault loop impedance, there was a big discussion in the industry. People started asking what exactly it is, because the word seems to be new for the whole nation. So I would like to show you some historic documents. For example, the IS 3043 1966. Please note, this is the first edition, 1966. Here, if you look at the clause number 11, measurement of earth loop impedance, the current which flow under earth fault condition, please note that during that time, residual current device or ELCBs are not very popular. The main protective device is a fuse. The current which flow under earth fault condition and will thus be available to operate the overload protection depends upon the impedance of the earth return loop. So the subject is, it's very clear. It is talking about the loop, the return path. Also, there is a picture to make the test of earth fault loop impedance. It was quite interesting. Probably if you have 1966 IS 3043, you can find this picture. This is in clause number 11. Also, the explanation, for example, clause number 12, industrial, commercial buildings, so on, basic requirements of earthing, you can see 12.1.2, the earthing arrangement of consumers installation shall be such that on the occurrence of a fault of negligible impedance from a phase or an earthed conductor to adjacent exposed metal, a current corresponding to not less than 3.5 times a rating of the fuse or 1.5 times the setting of the overload earth leakage circuit breaker will flow except where voltage operated earth leakage circuit breakers are used and make the faulty circuit dead. So the automatic disconnection of the circuit has been discussed since 1966. So it's not a new subject, in fact. Also, the same clause 12.12.1, the calculations are given. The Z means fault loop impedance, phase to earth voltage of the system divided by maximum fusing current of the fuse into the factor of safety. So currently, if we look at the 2019 version of the IS 732, the factor of safety is about 33%. I will show the calculation later on. Now, these are what I wanted to explain is this is not a new subject. It is there in our standards and regulations since old days. You can also go through the writings of these particular standard, the how to test, why to test, what to test, and all those informations are there in the standard. But one interesting information, once when we talk about the earthing in India, people always talk about 1 ohm. So 12.1.2.2, it is talking about fault loop impedance, and here it is again writing 1 ohm. I don't know on what background these are written. 1 ohm, the earth continuity resistance. So even today, the 2018 version of IS 3043 contains the same, similar wording, earth continuity. The maximum resistance of continuity resistance of the earth fault return path shall be less than 1 ohm. So all these are still there. IS 732 1989, section 5, inspection and testing. Of course, we don't have the habit of making an inspection and testing. That is a different case. But if you look at the section 5, inspection and testing, you can see serial number K. Earth fault loop impedance. There are several tests. For example, continuity of final ring circuit, continuity of protective conductors. In the new standards, A and B of 1989 has been clubbed together, and it is written one test. Continuity of conductors or continuity of wires. Then 1989 has got the test number C, earth electrode resistance. after this edition of 1989, this test, earth electrode resistance, has been removed from the standard. So in the new standard, you cannot see this particular testing, earth electrode resistance testing, especially for low voltage system, except at the point of commencement of supply under certain condition. But major, predominantly, if you look at the 2018 version, you can find here, one moment, I think I made a small mistake in the animation. Let me remove it, one moment. So here you can see on the left side the testings A to C. The earth electrode resistance testing has been removed and automatic disconnection of supply. So the systems are actually changing. Similarly, if you look at the CEA regulation, it has very clearly written, the NEC 2023 has very clearly written, IS 732, IS 3043, as well as the CPWD manual has included this particular testing, very, or stressed this particular test. To make the things easier for the user to understand the subject, in NEC, Part 1, Section 18, we have included a table which shows you the type of protective device such as an MCB. We have not provided the data of fuses and other protective device. Of course, in the next versions, probably we will include. So here you can find the type of the MCB and the rating of the MCB. Let's say, for example, you have a 32 amps MCB, type C MCB. The maximum allowed fault loop impedance is 0.48 ohm. Also, the calculations you can see here, 2/3. This is the safety factor. 2/3 of the calculated value should be the measured value. So basically, a lot of emphasis is given to this particular subject, which is automatic disconnection of supply, consisting of an RCD test or an earth fault loop impedance test. So I would welcome Mr. Peter to introduce the subject to the participants. Thank you very much. You can share your screen, Mr. Peter.
Okay, thank you very much. Okay, so hello everybody. My name is Peter Polik, and I represent here a Sonal company where I take care of trainings and technical support. So at Sonal we do different meters for measuring different electrical values, including a fault loop impedance. So I'm going to tell you why do we need to make this measurement. So a little bit of agenda. Well, pretty much Mr. Gopal Kumar, he explained about the standards, so I will be very quick about it. Then I will explain why we need to do certain measurements for the reasons of automatic disconnection of supply, and show you some of our products. So if we look at the international standards for testing, well, we will focus on the IEC 60364-6. But here in India, well, we need to look at the regulation of the CEA, so the Central Electricity Authority. And they tell us that we need to follow NEC, the National Electric Code of India, as well as the applicable Indian standards. Like here, there's the IS 732. Well, luckily for me, for the international environment, the IS 732 takes largely on the IEC 60364-6. As it comes for the equipment, well, it needs to fulfill these standards that you can see over here. So there's the IEC 61557, IEC 61010, which talks about safety of the equipment, and other requirements regarding electromagnetic compatibility. There's the IP code for the protection. So later I will get on with that. All right, so here we can see the screen from IS 732. And we can see here what measurements we need to do when we want to verify our electrical installation. And probably you are familiar with these measurements, but the new things that we can find over here, that's the resistance of floors and walls and the automatic disconnection of supply. So right now, quickly, when we will need to disconnect the supply automatically, well, in case we have a fault situation and there will be a short between a phase channel and the ground. So then we're going to have some dangerous currents flowing through the protective channel to earth, or there will be a possibility of electric shock to a person who's going to touch the faulty elements. So in this situation, to prevent fire or to save lives, we're going to need to automatically disconnect the supply. And here, for this reason, we will need to make the measurement of fault loop impedance. But later, I'm going to elaborate on this. All right, another measurement that was the resistance of floors and walls. So here the standard defines what probe we need to do, and the rest is pretty much same like other insulation resistance. So we're going to check the resistance between one point and another point of some insulation. We just need this special probe, so we can put it on walls or on the floors, like you can see over here. And we need to measure resistance of walls in case we have some metal conduits, then walls and floors also in case of some special workplaces. Here we can see there's some electric panel. In front of it, there's the mat. So if there's a fault situation, this guy over here, he will not conduct the currents to the ground. He's standing on insulating mat. So we need to check if this mat is working fine. All right. Now, if we look at into the NEC, the National Electric Code, we can find there that we have different levels of protection. So there's basic protection, which means basically that the dangerous parts shall not be accessible, and accessible parts shall not be dangerous. So for that reason, we use insulation on the live parts, we use some barriers and closures, or we put them beyond the reach of one's hand. Now, in case of a fault situation, the standard defines disconnection of power supply. And for that reason, we're going to need to check fault loop impedance. And there might be also additional protection, like additional equipotential bonding, or the RCDs, which we also need to check and make sure that their parameters are okay. All right, now as we look at the low voltage supply systems, and then we need to check the fault loop impedance. So we need to make sure that it allows the adequate flow of the current to operate the protective device. We need to test fault loop impedance to make sure that the automatic disconnection of supply is working. And its value depends on the type of the protective device that we are using. Also, we need to make the tests at the origin of the installation. So on the transformers, we need to check fault loop for each circuit, and we need to do this for all sources. Okay, so now let's look at the automatic disconnection of supply. Before I get there, let me quickly discuss different types of electrical grids. So here we have TN systems. In TN systems, the transformer is connected to the ground, and the active accessible parts of different devices their protective channels are connected through a transformer. Now, in case of a TNS systems, the neutral and protective conductors are separated. In case of a TNC, again, transformer is grounded. Accessible parts and covers here of different devices are connected through the transformer, but the protective and neutral channels are combined into one, so that's the PEN channel. And there's a sort of a hybrid, the TNCS systems. So once we look from the side of the power supply, from the transformer, first we have one channel called PEN, so protective neutral channel, which is later separated into neutral and protective channel. And additionally, protective channel has to be grounded directly to the earth at some point. Okay, now other systems, that's the TT system. Here, transformer, central point of transformer is grounded, and the conductive accessible parts of different devices are also grounded, but locally. So here the P channel does not go through the transformer, it just goes locally to the ground. And there's also the IT system. So over here, the transformer is insulated from the ground. And if we have any accessible parts of covers, they are grounded locally. Now there might be different IT systems with or without neutral conductor. Okay, so I talked about different systems. Now let's look what is going to happen in case of a fault. So if everything works fine, then we have here our device. It is powered through current flowing through a phase channel to the device and returning through the neutral. All right, so everything is nice, but what in case of a fault situation? Well, we're going to have a current flowing through a phase channel to our device. And because of a fault over here, we're going to have some potential of the cover of the device, which is going to be led to the earth through the protective channel. So through the PE channel to the earth, either directly to a transformer like in TN systems or in TT through the actual ground. Or in case some unlucky person is touching the cover of this device, well, then the current will flow through their body and to the earth. So what are the dangers in this situation? Well, we can face some overheating leading to a fire. Or if the person is touching, then they will get electric shock, and in the worst scenario, they can die. So we want to avoid it, and for this reason, we automatically disconnect power supply in case of a fault. And for that reason, we can use RCDs, we can use MCBs, or we can use some bigger circuit breakers, for example, directly at transformer station. Okay, and here we have some examples of the fault loop. So we have a fault situation and our loop with the current flow. Here it is. So that's in case of a TN system, it returns through PE channel. So that's in the wire in the wall directly to a transformer. Or in case of a TT system where the grounding is locally, then the loop will close through the actual earth, actual ground. Okay, so now in the IS 732, we have described different types of protection. And in case of a single fault, so single short between phase and ground channel, we have the automatic disconnection of supply. So that means that the power supply should be disconnected. Well, what is the time for the disconnection? Again, we're going to look into IS 732. And depending on the type of the system that we have, on the level of the voltage, the supply voltage that we have, we are going to have different times. So here, let's make it simpler. Let's just look at the table. And let's say typically we have the supply voltage of 230 volts AC. So in case of a TN systems, the disconnection time is 0.4 seconds. And in case of TT system, we have 0.2 seconds. Okay, so this is the time in which our MCB or RCD or some bigger circuit breakers should work. Okay, now what is going to make them disconnect in this time? Well, obviously the current. So let's look over here. We have characteristics of different breakers. Let's look, for example, at characteristic C. Here we have time, seconds and minutes, and here we have the multiplication of the rated current of our safety device. So let's look at MCB type C for 0.4 seconds over here. the multiplication for AC network, the multiplication of the rated current is between 5 and 10. So, for example, if we have an MCB C16, then the disconnection current that will make the MCB work within 0.4 seconds, that will be 10 times 16. So for C16, 160 amps will be the disconnection current. Okay, here we have some examples. These are some older breakers. Right now we have automatic ones. Okay, so we know right now what is the level of the current that triggers our MCB or RCD or other breaker. But what do we need to make it actually trigger? Well, then the fault current flowing here in this circuit has to be higher than the current triggering our breaker. Okay, now we are unable to measure fault current flowing in the circuit directly. This is just physically not possible. So here, okay, let me simplify this. Right now, let's look at our supply voltage and a fault loop resistance. So voltage over resistance, that is giving us the current. However, this is a simplification in case of a nice DC system here. But in case of the AC systems, we need to measure fault loop impedance because we are expecting that in our systems there will be some resistance coming from, for example, wires in the walls. But our transformer also have some coils, so it will have some reactance part. And that's why we measure the impedance, which is the summary of resistance and reactance. And further on in our network, we need to know the fault current flowing in case of a fault situation, and that is going to be our supply voltage divided by the measured fault loop impedance. And this is the fault current or prospective short current. Okay, so right now we have current triggering our breakers in a desired time, and the fault current which is flowing into our in our circuit in case of a fault situation. So we need to compare the two, and if the fault current is higher than the current triggering the breaker, that means that evaluation of our network will be positive. Now in the IS732 you can find all these three equations. So obviously we cannot measure fault current, it has to be calculated. So we can measure the supply voltage, we can measure fault loop impedance, and the calculation of the two will give us the value of fault current. So let's look at the example. We have our network. Let's say this is a TN system, so with 230 volts AC. So the disconnection time is 0.4 seconds. That's the required time for the automatic disconnection of supply. We are having here the MCB type B16. So for B, this will be 5 times 16. So the 80 amps, that's the current which will cause our breaker to disconnect within 0.4 seconds. And we have performed a measurement in our circuit. We got the value of fault loop impedance of 2.041 ohm. Okay, now is it good or bad? Well, here the test technician needs to evaluate the situation. However, in our meters of some higher models, like for example, Sonel MPI 540, it has a built-in database of different breakers. We can put their B16, and after the measurement is finished, the meter will automatically evaluate the result for us. But well, anyway, still the final decision is based on us, the test technicians. So we got the fault loop 2.041. Is it good or bad? Okay, so we take our supply voltage, which is 230 volts, divided by 2.041 ohms. And that gives us the value of 112.7 amps. So this will be the value of current flowing in our circuit in case of a fault situation. Now, is it going to trigger our B16 MCB? Well, yes, because B16 is triggered by 80 amps in 0.4 seconds. So our fault current is higher than the current triggering our breaker. Okay, now further on, the meters can automatically calculate for us the value of fault currents. But what value of voltage shall we use? Because to calculate the fault current, we need to know the value of supply voltage and the measured value of fault loop impedance. The impedance is just measured, and the supply voltage we can select either UN, so the nominal voltage, like typically in India, that's 230 volts, or U0, which is actually the actual measured value of the voltage. So here we're going to select the lower one, because that will give us, as the result of the calculation, lower value of the fault current, and therefore our conditions will be more strict. So let's say in case we are somewhere close to the transformer and the value of voltage in the socket will be 240 volts, then we're going to select for the calculation the nominal value, which is 230. On the other hand, when we are far away from transformer and the measured value of voltage in the socket will be about 220 volts, then we need to use this actual measured value. Okay, now what in case we want to measure a fault loop directly on a transformer? Well, for this reason, we're gonna need to use more precise and more powerful meters, because then the let's just say whole distance of the loop will be very short, because all the wires will be very short that we need to measure. And for this reason, we have our high models of fault loop meters. So the MZC series in Sonel, and that will be MZC 310, 320, or 330. So here you can see the model 310. And what's so special about them? Well, they use a high measuring current, and they are using also a 4-pole method, thanks to which we don't need to worry about the resistance of the test leads. We can just connect directly here between phase and the ground channel and perform the measurement. Now, what in case the value of the impedance is just too high, which may often happen in case of a TT system? Then we need to use additional protection in the form of RCD, so the residual current device. Also, the standard IS732 allows us to adopt the triggering current as 5 times the nominal current of the breaker in case we miss some data or we don't have the adequate information. Okay, so now in case we have networks secured with the RCDs, how do we check the disconnection time? Well, here we need to measure the resistance, which is the sum of the earth resistance, so the resistance of the earth electrode, and the resistance of the protective conductors. So everything that goes from the actual ground through the wall in our building up to our socket, this is the resistance, and we multiply it by the value of the rated residual current of our RCD. And this value should be lower than the long-term permissible voltage. So as the IS732 describes, 50 volts. So that's how we calculate the disconnection in case of a TT network secured with RCDs. And here we have some examples. So depending on the rated current of the RCD, these are the maximum values of the resistance of earth electrode and the resistance of the PE wires in the walls that we can get. So for example, when we have the RCD with 30 milliamps current, then the maximum value of resistance of earth electrode and the wires in the wall, that will be 1667 ohms. Okay, so to summarize the automatic disconnection of supply, here we can see the conditions to check the effectiveness. So in case of a TN network, well, we measure fault loop impedance, we calculate the fault current, and fault current should be higher than the current triggering our breaker within the time described by the standard. So again, this could be MCB, RCB, or some bigger breakers. Now, in case of a TT system, when we have the overcurrent protection, that's the same as in case of a TN. And when we have the RCD protection, then we need to check the earth resistance of earth electrode and the resistance or the continuity of our protective wires in the wall, and multiply them by the rated current of the RCD. And this value should be lower than the long-term permissible voltage, so the 50 volts. And further on, in case of the IT network, well, here, well, the transformer is insulated from the ground. So in case I would grab the phase channel, well, nothing will happen. So here we need to consider a 2-point short to the ground, so that our fault loop could be closed. And here we can have different types of IT systems with or without a neutral conductor. And these are the equations describing the effectiveness condition. Okay, now further on, if we are using our top models, so like MZC 310, 320, or 330, the fault loop impedance meters, then besides of checking the value of the impedance of fault loop or calculate the fault current, we can also check the touch voltage and the shock touch voltage. So those will be the voltages between the cover of our device and main grounding rail or actual earth. So in theory, this value should be 0. In practice, we can have some single volts, but in case we have some faulty construction of our electrical network, then we can expect some higher values of voltages. If we find those, then we need to well, check the construction of our network and find where are the problems. Another situation is what in case we have some converters like rectifiers or inverters. What then? Can we measure fault loop impedance in that situation? Well, unfortunately, this is physically impossible, but in that situation, we are going to check the continuity of our protective channel. And then similar like in case of the RCD protection, we're going to take the resistance of the protective wire, multiply it by the tripping current of our protection, and this should be lower than the long-term permissible voltage, so lower than the 50 volts. Okay, so now let's look at a few examples. We are going to measure fault loop impedance. Here we are in a TN system. First example, we are closer to transformer. Second one is we are further away from transformer. So the question is where the value of fault loop impedance will be lower. Okay, a little time to think about it. And now the answer is that lower value we are going to have closer to a transformer. Why is that? Well, we are measuring impedance of this loop. So that's the resistance of the wires, reactance of the coils in a transformer. But look over here, the wires in our network, in our walls will be just shorter. Here they are further away. So, well, obviously the resistance of the longer wire is higher than the resistance of a shorter wire. So that's why the closer to transformer we are, the lower will be the value of measured fault loop impedance. Another example where measured fault loop impedance will be lower in case of a TN system or a TT system. Okay, so here lower value will be in case of a TN system. Let's look over here. This is our fault loop, the red dashed line. And in case of a TN system, it is closing through a protective wire, so just a piece of metal in insulation. In case of a TT system, here the earthing is provided locally, So our loop will close through the ground, the actual earth. Well, obviously a piece of metal, like in case of a PE wire, has a lower resistance than the actual earth or dirt. So that's why lower values will be in case of a TN network. And finally, third example, where will be lower value of measured fault loop impedance in case of a TN network, but here we have a broken PE wire or a TT system. Well, in this situation, measured values will be about the same. However, it is important to us, to test technicians, to know what kind of system we are measuring. Because in case of a TT system, evaluation will be positive. But in case of a TN system, here we would know that our results are just too high and that our PE wire is broken at some point. And that's why the loop is closing through the actual earth instead of the wire that goes through the walls. Okay, and here we can see the screen of our meter, Sonel MPI 540. So this is our multifunction meter. Right now, this is the highest model. So let's see what we can find out on the meter. After we perform a fault loop impedance measurement, well, obviously we can see the value of measured impedance here between phase and ground channel. So as the standard describes, IS732 describes a short between phase and the ground. On the side screen, we can see the components of this value. So the resistance, the reactance, actual measured value of voltage, and actual measured frequency of our network. Now, in case of our higher models of the meters, like here the MPI 540, we have a database of the breakers. So in this particular situation, the breaker used was a B10. So we enter it over here from our database, and the meter knows that the current triggering B10, that's 50 amps. Further on in the meter, we'll calculate for us our fault current. So here we can select what calculation method we are using, either nominal voltage or the actual measured voltage. Here the actual voltage is 241 volts, so we use UN, the nominal voltage of 230 volts. And 230 volts over 2.098 ohms, that's 109.6 amps. So this is the fault current flowing in our circuit. And obviously fault current is higher than the current triggering our breaker. That's why the meter has evaluated the result as positive. That's why we can see green check over here and on the results in green. In case of a negative evaluation, we would see all these values in red. Okay, now further on, in case we would like to provide thermal protection in a three-phase network, then for these calculations, we need to use the 2/3 of the measured fault loop impedance. Okay, so that was a protection in case of a fault. Now let's look at the additional protection. So the equipotential bondings and RCD parameters. So first, equipotential bondings. Here the standard tells us to measure it with the test current of at least 200 milliamps, and the flow of the current during the measurement has to be in both directions. So, well, basically these days, all of the modern meters that allow for continuity measurement can perform it this way. And in practice, how does it look like? We're going to connect a meter with one of the test leads to the main grounding rail. And then with the other test lead, we are going to go and touch the protective channel in every socket or at every device which is connected with the PE wire. And this is in order to make sure that our PE wires, protective wires, they conduct well, and to make sure that they are not broken. Now, before we start this measurement, we need to auto-zero the test leads. So to get rid of resistance of the test leads, Well, I mean, you can imagine that sometimes when we go from main grounding rail to different sockets, it could be a longer distances. So we don't want to measure the resistance of our test leads, just the resistance of the wire in the wall. Okay, and finally, let's move on to the measurements of the RCD parameters. So how does it work? Well, we put the RCD between phase and neutral channels, or between all three phases and the neutral. And if everything is fine, that the current flowing through the phase channel powers the device, and the same value of the current returns through the neutral channel. The RCD sees that there are no differences between the current flowing in on a phase and flowing out on the neutral, so it will not trigger. But in case we have a fault situation, then the current flowing in and powering our device will divide. Some will return through the neutral channel, and some will return through the ground channel to the earth. Now the RCD will see that the current flowing in on the phase and flowing out on neutral, they are not equal. So then it's going to trigger, and it's going to break and disconnect the power supply in our network. So here, when we want to measure the parameters of the RCDs, we have the following parameters. We can check what is the residual current. We can check what is the triggering time for the RCD. And we can also check what it will be the resistance to earth and touch voltage. Here we can see an example of an RCD. So that's how it looks like. It has a nameplate with values of the currents. It has a switch, and it has a test button. Now we can divide RCD types into different groups, depending on the shape of the current that will trigger them. So the simplest ones are the AC type, which work with the sinusoidal AC current. However, in the new electrical installations, we should no longer use those. Now, why is that? Well, we have plenty of different computers, different electronic devices. Well, for example, even my laptop or my monitor over here are powered by the DC current. So we can expect that I'm connecting rectifiers. Rectifiers will cause some harmonics in our network. So that's why the fault currents will not have a nice sine wave. They will have some sort of distorted signals. So that's why we have RCDs of type A, which work with sine wave AC and pulsating DC up to 6 milliamps. We have type F, which works with the sinusoidal AC, pulsating DC, and composite of multi-frequency up to 10 milliamps. B type that works with the sine wave, pulsating DC, smooth DC, and composite of multi-frequency up to 1 kilohertz. And B plus, same like B, but up to 20 kilohertz. Now we can also divide RCDs depending on their triggering time. So the general ones with no delay, short delay ones with idle time of at least 10 milliseconds, and selective ones with idle time of at least 40 milliseconds. So once we look at the characteristics of this RCD, here we can see the tripping time, and here we can see the differential current. So for the general use, this RCD, we will look at the green field here on the specs. So for example, when we have the rated current here, 30 milliamps, the disconnection time will be between, 0 up to 300 milliseconds. As we increase the value of the current, then the disconnection time will drop, but still starting from 0 just to the lower values. But if we would like to use this RCD as a selective one, then we need to look at the orange field on the graph over here. So for the nominal current, 30 milliamps, it will trip from 10 milliseconds up to 300 milliseconds. And we can see that there's the border over here. The tripping time starts from 10 milliseconds. And similar, in case we would like to use it as a selective one, then we look at the blue field over here. Okay, and with our multifunction meters of MPI series, we have there a special function called RCD auto measurement. and it allows us to check all the parameters of the RCDs, and also RCDs of a different types, AC, A, F, B, and or B+. So here we can check the triggering current, triggering time of the RCDs for nominal current times 1, 2, or 5, or half. In case the RCDs trigger when we tested with the value of half the nominal current, that means that it is too sensitive and therefore faulty. Further on, we can check the RCD with different shapes of the current signals. Here we can see only the sine wave, but once we move the bar up, then for types A, F, or B, we would be able to see that the RCD was tested with all different shapes of signals. And also we can change the polarization of the signal, so depending if we have a minus or a plus here at the end. So in case of a sine wave, minus starts with the falling slope and plus starts with the rising slope. And in case of pulsating or DC, that's just the polarization. Okay, so we have made all our measurements. Now let's look at our measuring equipment. So once we look into the IS 732, it says that the meters, they should comply with the IEC 61557. And the standards is a multi-sheet standard. Each sheet describes different types of measurements. But what is important to us as test technicians, this standard describes the maximum permissible error. So this is the maximum value of uncertainty which is allowed over here. If the result of our measurement carries a higher uncertainty or higher error, then we are not allowed to put it into our report. If the value is lower, then we can put it into our report. And now it is important to look at the technical specs of our meters and check their measuring ranges. Because we can all imagine that the display range on the meter starts from 0 up to a certain level, but the measuring range, including the error defined by the standard, well, it is connected with the accuracy of the meter. So plus minus a few percent of the measurements, plus a few digits in case of the digital meters, but then the values closer to 0 will be carrying uncertainty well higher than the ones described here by the standard 61557. So we look at the technical specs of the meters, we check their measuring ranges of the meters, and they will never start at 0. They will start at a certain value and go up to maximum range of the meter. So we need to remember to check those. Okay, and so now a little bit about our history. So the company is nearly 30 years old right now, and this is the first meter that we have made, MZC1. This is the man who made this meter, Mr. Jan Walulik. He used to be our, well, the vice president of our company for many years. Just recently he has retired. And this meter is a meter for measuring fault loop impedance. So you can imagine that we do have some history about this particular parts of the norm regarding fault loop measurements and regarding the automatic disconnection of supply. Now the time has moved on and we have newer meters. For you, I would recommend our multifunction meters because it's a single tool that can allow you to measure a whole electrical installations in buildings. It could be industrial buildings, commercial buildings, some office facilities, as well as residential buildings. So this meter allows us to check insulation resistance, earth resistance, to perform fault loop impedance tests. It also has a built-in power quality analyzer. So there's a three-phase power quality analyzer of class S. We can check parameters of the RCDs. We can check the rotation of the phases. And we can also check the light intensity. So that many functions in just this one device. Now, in case the multifunction meter is too much to you, then you can look at the single function meters as I was showing this to you over here. Or in case you are working for power utilities where you need to measure some bigger power objects, like, for example, measure fault loop impedance directly on a transformer, or measure insulation resistance of some medium voltage cable, well, then the multifunction meter will not be powerful enough. For this reason, you may want to look at single function meters, which are just more powerful. They have higher measuring ranges, they have higher test currents or voltages, and that would be the right solution. Now, coming back to our multifunction meters, at Sonel, we have a big choice of all different multifunction meters, from the simple testers like MPI 502 up to our current flagship, which is MPI 540 PV. And they can perform all different types of measurements. Each meter can check voltage, frequency, continuity of protective channel, measure fault loop impedance, and RCD parameters. Well, here just the types of measured RCDs differ on the meters. Now, further on, in case we would like to measure electrical installations in building, we can check, for example, MPI 506, which can also check insulation resistance, phase rotation, and meters like 507 or 520. These models can also check earth resistance. And further on, each model has some extension. Right now, our higher models allow us to check all parameters of electrical installations as described by the IS 732. Also, in case of car charging stations, because we can check the EV type of the breakers. It has a built-in three-phase power quality analyzer of type S. And it can also check the safety of photovoltaic networks. So PV here stands for photovoltaic. And a little bit about photovoltaic networks. So here, the standard describing safety measurements, that's the IEC 62446. And it says that first we need to check the AC part of the network to which our photovoltaics is connected. And we do this according to IS 732 and NEC. And then we look at the DC part, so the actual photovoltaic panels, where the standard IEC 62446 describes the measurements. And there are measurements of category 1, category 2, and additional tests. Well, category 1, these are the mandatory tests, and that's the continuity of the protective channel, polarity test, combiner box test, open circuit voltage and short circuit current, functional tests, and insulation resistance on the DC side. Optional tests are category 2 and additional ones, and they include current voltage curve, thermographical tests, and additional tests, voltage to ground, blocking diode, insulation in wet conditions, and shade evaluation. So we can do all of that with our multifunction meters MPI 540 PV. However, if you are making tests only on photovoltaic installations and you are not interested about all the AC part, you can look at our PVM meters. So photovoltaic meters. These are designed only for the photovoltaic installations. All of the meters, they can perform the test of category 1. The PVM meters, they can also make tests of category 2 or additional tests. And also one more meter that I would like to get your interest, that's the portable appliance testers of PAD series. So here I was telling you about checking continuity of the protective wires, but I was focused on IS 732 NEC, so we are focusing on the part of wires in the walls, right? Now, what happens between the actually conductive parts of the covers of our device and the point in the socket where we connect to the PE channel? Well, there's the PE wire in the power plug of our device, power cable. And here it is also a good idea to check its continuity. That we can do with the portable appliance testers. We're going to connect our electric device to the socket on the face of the meter, and then with the probe touch the accessible conductive parts of the covers, so different metal parts of the covers, and make sure that this PE channel within our device is working correctly and that it is not broken. Well, here on the screen you can see a European socket, but we have different sockets available for the meters. Besides that, with path meters, we can also check other parameters of portable appliances. Besides the continuity, we can check insulation resistance, leakage currents, power tests, IEC cable tests, so we can make sure that our electrical devices are safe. And that's the result on the screen. Okay, so let me quickly just follow up and let's get to the end. What we need to do according here to the CEA regulations, who is responsible for all the electrical tests? Well, the owner of electrical installation, so the applicant here. It's not the electricians who are building it, not the test electricians, it's just the owner of the building, owner of the construction, like for example, charging station. They are responsible for all the installations within their ownership, so also the electrical installation. And for this reason, well, for example, me as a homeowner, I would have to call a chartered electrical safety engineer, and that's the test technician who will come with the meter and verify my electric installation. And right now, the standard defines two types of verification of electrical installation. There's the initial one, so after the construction of the building is finished, or after the modification, construction to electrical installation are performed. And we do this to make sure that everything was constructed properly and is working safely. And later we perform periodic verifications. So then, well, depending on the type of the premises that we have, depending on the type of the building, we need to call for this chartered electrical safety engineer to come and check our electrical systems, our networks, and make the appropriate measurements. All right. So a little bit also about us. So Sonel company, we were established in Poland in 1994, so nearly 30 years. And then our branch office in India was established in 2013, so nearly 10, well, right now it's 10 years. In India, we have over 40 distributors, as well as our own sales force. We also hold locally the laboratory, and we locally hold our repair services. So in case you have our meter, it breaks down, you can locally send it for repairs. Our branch office, together with our service and laboratory, is based in Chennai. So that's in Tamil Nadu. And we do different meters here. We have the multifunction meters, we have insulation resistance meters. Our insulation resistance meters are pretty powerful and resistive to different interferences. We also have meters to measure fault loop impedance or earth resistance. So here you can see some of the examples. We do meters for power quality, micrometers, thermal imagers, lux meters. Okay, and we sell to different customers within India. We have recommendations from them. If you would like to check all of the instruments that we do, go to website sonel.in, and there you can see all of our instruments, as well as we provide different trainings, and that's usually me. And here's the contact details to Mr. Shyam Ravindran, who's the managing director of our Indian branch. Okay, so thank you very much.
Thank you, Peter. Now we open this forum for question answer. I would like our moderator, Mr. Gopakumar, to take up the question answer session. So we'll say exactly we have 12:10, so 20 minutes, 25 minutes for Q&A. So I think we have more than 15 questions lined up. So I will open the forum for question answer. Over to you, sir, Mr. Gopakumar.
Yes, thank you very much, Mr. Dominic, and thank you very much, Mr. Peter, for a nice presentation. So this was actually our first experience in NFE platform where we are talking about a product or a company, something like that. So, great experience and also a lot of information to our participants. We are also happy to see that our webinars had become really international. I could see participants from all over the world, from Philippines, from UK, from Europe, from USA, from Africa, and so on. So and hundreds of tens of hundreds of participants. So it's great.
And we also have from Middle East, there are a lot of Middle East companies, like some construction companies also participating. I think we have 25% outside India for this show. It's nice to see we are going global. It's not, NFE is not for India, it's for global.
That's a good news. Thanks, Mr. Dominic. So we have few questions, Mr. Peter. The first question is, in case if the from Mr. Satyamurthy, in case if the measured fault loop impedance is high, how to reduce the same?
Okay, well, first of all, we need to make sure that this is just a natural situation, that our P channel is not broken. So for this, I will just check the continuity of the P channel from one connection point to another one and make sure that that it is not broken. But if the fault loop impedance is high as just a natural situation, then I would have to use additional protection in a form of RCD. So then I will be looking at my fault loop from the RCD to the device and back to the RCD. And well, then I will be able to make sure that it triggers in case of a fault situation.
Yeah, thank you. Actually, with an Indian context, I would like to elaborate this answer a little bit more because I have found in a lot of cases the protective devices are overrated. 3 days back, I was checking a case where the protective device, it's an MCB, C-type MCB, rated for 63 amps, and the circuit wire, the outgoing of the protective device, the wires are 2.5 square millimeters wire. So this is not related. So for with an Indian context, not only the to reduce, first we should check what kind of is the rating of the protective device proper. Does the wires, the current carrying, the live conductors are properly rated? Then we have to check whether the return path of the fault loop is not having any loose contacts and so on. So with Indian context, we have to do a thorough check of the entire circuit. So would be better. Thank you for that. Now the next question, Mr. Ahmed, at which point of fault loop impedance test to be carried out, at the distribution board or at the socket outlet?
Okay, so here when we look at the CEA regulation, well, we have this regulation has like the 3 points at which we look to look. So once we need to look at the origin of installation, so that would be at the transformer station, and then is the fault loop impedance tested for each circuit. So okay, and the first one says is it tested for all sources. So on the transformer, well, here the supplier, the owner of the transformer should make sure that everything is fine. And then in case of a building, we should test it at each socket. Or in case we have car charging stations, every station, and also every socket on the station. And if we have many sources, so from many transformers, then for each source, we have to test this.
Okay, thank you. Now another question. Can we measure the loop impedance of a 3-phase 415-volt induction motor which is in running condition at site? Similarly, can we measure the loop impedance of the transformer LV side when the transformer is in service? So basically the question is, can we do the measurement once when these devices are in working condition?
Well, yes, here, when we are measuring fault loop impedance, we do it on the energized network. So there have to be voltage present. But to extend this, in case we would like to follow all of the tests that we do according to the NEC, there are some tests on the live networks, some on the de-energized ones, like, for example, insulation resistance or the continuity. So we need to assign, I don't know, a few hours or a day to perform all of these measurements and to make sure that we will be able to turn our network on and off. Yes, so energized and de-energized. But as it comes to fault loop measurements only, we perform them on the energized installations.
Yeah. Thank you. So it has to be carried out in on condition. The system energized the condition. Now we have a question from Mr. Desai. Can armor of XLP cable be considered as ground wire conductor to carry prospective fault current in TNC system? What should be the earth loop impedance in this case? There are two parts of the question. The first question is whether you see in India, we always use armored cable. There is a steel armoring in the cable. The question is whether this armoring can be used as a fault return path.
Okay, I'm not entirely sure about the construction. I mean, if the standards allow to do this, then yes,
Yeah.
but okay, I'm not so sure about the construction part
I
here.
will answer this. The practice in India is a little bit different in other countries, because in Europe, inside you use an armored cable once when there is a chance of a mechanical damage, whereas we use it everywhere, all over for example, industries inside the factory, inside the premise also we use armored cable. So if we look at the standard point of view, the IS 3043, we cannot very clearly say that the standard allows to use armoring as a fault return path. Here the problem is the termination of the armoring. We are not sure. There is an IS standard for cable glands, and the cable, that's particular standard, of course, it's from IC. So the standard explains that the gland should have tested parts to carry substantial amount of fault current, but those kind of cable glands as well as those kind of systems are not available in India. If we look at the most of the terminations of cable gland, probably 50% of the cases, the glanding itself is not correct. So the better way is to have a separate fault return conductor, since we are not sure about the integrity of the fault current carrying capacity of the armor, as well as the availability of these clips, clamps, to ensure that the armor is connected properly to the MET or the earth bus bar. So that is the answer. Thank you very much. Now we have Mr. Ashok Suman, is the meter test with phase wire live? Yes, Mr. Ashok, we have already answered it. It's on live condition. How do we calculate maximum allowed fault loop impedance in case of RCD? Over to you, Mr. Peter.
Okay.
How do we calculate maximum allowed fault loop impedance in case of RCD?
All right, so that's well, similar situation like okay, first, like in case of the MCB, so we're gonna look at the disconnection time for our electrical installation, which is required by the standard IS 732. Then we're gonna check what current triggers our RCD or MCB. We're gonna measure fault loop impedance, take our supply voltage divided by the measured fault loop impedance, and that is our fault current. If fault current is higher than current triggering the breaker, could be MCB, RCD, or some bigger circuit breakers, then it's good. Also, another situation, in case we are using RCDs as additional protection, then we need to measure the resistance of the earth electrode plus the protective wire all the way up to our socket. And then this resistance times the nominal current of the RCD should be lower than 50 volts, so lower than the long-term permissible voltage. And that's what we find in the standard. And here, particular values, they depend on well, particular installations, how they were designed, constructed.
Yeah, actually, to make the answer simple, you can refer to IS 3043 2018. There, the calculations are given in a TT system, and if you use an RCD, what to do is explained. But what you should understand mainly is a very important clause from IS 3043. Let me read it. It says, clause number 23.1, basic protection, basic purpose of earth fault protection. I just read it. The clause number A says the earth fault loop impedance has to be low enough to allow adequate earth fault current to flow to cause an overcurrent protective device, for example, a fuse or a circuit breaker, in the faulty circuit to operate in a sufficiently short time. That means if the fault loop impedance is lower, then you can trust an MCB or an OCPD or a fuse. Now the second line, it says, or where it is not possible to achieve a low enough fault loop impedance, disconnection may be initiated by fitting a residual current device RCD of 30 milliampere rating. So the two options given in IS 3043 is, if you have a OCPD type of device, you check the fault loop impedance and ensure that the device is able to disconnect. If this test is failing, you put a 30 milliampere RCD. Is probably this is not from the IEC or from the European point of view, but this is an Indian point of view. So the system is the standards are a little bit different in this particular case. I hope the answer is clear. So is earth fault loop impedance mandatory in continuous process fertilizer industries? Of course, yes, because now the regulation says you must test the fault loop, or you must ensure automatic disconnection of every circuit in case of a fault. And then once when automatic disconnection is important and requirement, then you should do the test. So it isn't the type of building, like hospital, this kind of building doesn't need it, or that kind of building need it. That kind of categorization is not there. If you are using electricity, you should do the test. Very simple. So now there is another question from Mr. Prafulla. Recommended values of loop impedance for MCB is given. Kindly give same value for DIN type GL fuse. Okay, Mr. Prafulla, the better way is you can get the disconnection curve of the protective device which you are referring, and you can get those information from the manufacturer's catalog. So we have another interesting question. In TT system, which is common in India, when the measurement of fault loop impedance is done, earth electrode resistance comes into picture. Hence, we can say that even though measurement of earth electrode resistance is not important, maintaining a low resistance for earth electrode is important, so as to keep the fault loop impedance low. Hope, Mr. Peter, you are able to see the question. You can read the question. So, would you like to answer this?
Okay, yeah. So in case of a TT system secured with the RCDs, we do need to check the resistance of the earth electrode and the resistance of the protective wires. Well, yes, in this situation, we need also to make sure that the earth resistance of the earth electrode is low.
Yes, actually, if we look at, if we connect it with the wording from IS 3043, which I read just before, clause number 23.1. So here the requirement is, if the fault loop impedance is failing, you have to anyhow put a 30 milliampere RCD. So if you put a 30 milliampere RCD, testing that RCD becomes more important rather than testing the earth electrode resistance. This is the way I would read, because earth electrode resistance is not written exactly in the IS 732 for this particular automatic disconnection. So I hope the answer is clear. Now we have the question from our General Secretary, Apau sir. What is the confidence level of accuracy prescribed in IEC 61557? Is it 95% or 90% or any accuracy is prescribed?
Yes, it describes the, maybe I will share my picture. Okay, so yeah, here I have the picture. There are different parts of the standard describing different measurements, but it describes the maximum permissible error. So what does it mean? The meters, they have accuracy described as plus minus a few percentage of measured value, plus a few digits. And well, when we would look at the low parts of the display range, then especially errors from the digit will constitute a big percentage values. So, well, yeah, so here basically we have the maximum error, which is described by the standard. And well, we need to make sure that our meters comply with this. Also, in technical specs of the meters, in their manuals, we can find what are the measuring ranges according to the IEC 61557.
Yeah. Actually, these maximum allowed ranges, which is given plus or minus 30%, is itself gives a very good indication. Now, if you look at the standard, there are safety margins already inbuilt in the standard. As a result, even if the values are plus 30%, for example, the disconnection is ensured. That is how it works. So now, Mr. Ramakrishna, what are the suggested remedial measures checks to reduce earth fault loop impedance if found to be high during measurement? So, Mr. Ramakrishna, here, as I said, in most of the cases, in the Indian context, the values are quite high because a lot of cases our protective devices are overrated. Overrated in the sense you actually need a 10 amps MCB, but the MCB installed is 63 amps and 2.5 square millimeters of wire. So first you should check whether the circuit is in proper condition, the devices are properly rated, the wires are properly selected, the voltage drop is within the range. Then you should check the continuity of the fault return path. So if everything is fine and if the value is higher, probably the fault return path is having some loose contacts. You should check that, as Mr. Peter already explained this. To the next question, Mr. Vishal, if we have a series of distribution feeder pillar in between supply transformer and service installation, then how do we measure fault loop impedance? Will it involve all feeder pillars or only the feeder pillar closest to the service installation? Actually, the question is not very clear to me. If we have a series of distribution feeder pillars in between supply transformer and service installation, then how do we measure fault loop impedance? The impedance is measured at the point where you are making the measurement. Say, for example, in a circuit at a socket outlet device, we are making the test. Or in a terminal of a distribution board, we are making a test. So the impedance of the entire circuit is measured. So the number of distribution feeders is immaterial in this particular case. It may be one feeder or maybe the distribution pillars in between the transformer and the consumer premise. It can be one or so. The test is basically carried out for the entire circuit. You should check the circuit actually. I hope my answer is clear, Mr. Peter.
Yeah. Just I'm thinking if you are further away from the transformer, then all these wires on pillars or in the ground, there will be longer. So you can expect higher values.
Yeah. So now what I could see in slides in the person are doing testing activities with kit in bare hand. Nobody uses hand glove. Is it a requirement for safety person or no need to use while using zonal make device? Oh my goodness. So you have to answer this.
Okay, well, obviously you need to wear safety equipment when you are making the measurements. I'm just thinking right now, I'm looking here back at my picture. I don't know, maybe that one was just made for some marketing reasons and the guy didn't wear gloves, but normally when we are working on electrical installation, plus for fault loop measurements, it's an energized one. well, obviously we should wear protective gloves. I know that there are some other rules describing safety of personnel, and that depends on what type of electrical network we are working. Maybe some of my pictures weren't clear enough. In case on the insulation resistance, because there was guy measuring floors and walls, well, that's on the de-energized object. So that's a different thing.
So anyway, we will take care of it. Now, actually, we face a small problem in India. For example, the gloves which is rated for electricity, certain voltage, these gloves are sometimes very much uncomfortable to wear and put, hold a clip, clamp, and do the testing. So as a result, I have seen a lot of cases people try to avoid it, which is not correct. So we have a question from an anonymous attendee. Normally, we don't take up the questions from anonymous attendee, but still, let us say, my question is that fault loop impedance measurement have a definitely have a relation with the linear measurement length of circuit in wire of different size of conductor. Do we have a data that what is the length of wiring restrictions in the building to make fault loop impedance within the range at the time of planning and execution of the work? The answer is very simple, sir. This is also related to the voltage drop. You should your circuit should be within the voltage drop limits. So, Mr. Peter, you would like to answer this?
Okay. Well, I think we will need to look here at the construction part and the design part, because, well, obviously this also matter how thick the wires you are using. That will be the influence, but okay, I know more about the measuring part, so I just know that we need to comply the requirements of the automatic disconnection of supply. So the disconnection required time. But here, of course, we need to look at all the components that we are using, the thickness of the cables, their lengths, and so on. That will have some influence here.
Yeah, thank you. Now we have another question. Right from 1966, the measurement of fault loop impedance is mentioned. Then why all these earth pits and related extravagances? In the present scenario, can we disconnect all those unnecessary installation and refill the earth pits employing the right tripping protective device on fault occurrence? I think still the electrical inspectors insist on the old practice. Do we intervene? I don't know who has asked, because this question is from an anonymous attendee. I don't know whether you are powerful enough to intervene. If you can intervene, then probably it's a good idea to intervene and tell the electrical inspectors that you should insist for this particular test. But the first part of the question, the earth pit, I really don't know from where the ideas of so much, earth pit measurement and the earth pit resistance. Mr. Peter, for your information, in India, every earth electrode we measure the resistance, during a dry day and paint it saying that the earth resistance is 1.002 ohm. So the meter itself can have 30% accuracy, plus or minus. I don't know why such an accurate measurement is made and written 1.62 ohm. So you can find this information. Now, answer to the question. You cannot disconnect the earth electrodes. You need it. What you don't need is the measurement of the earth electrode resistances, and trying to reduce the earth electrode resistances can be avoided. Earth electrodes are, of course, required. The reason is, as I said in the beginning, the protective measure is protective equipotential bonding and automatic disconnection of supply. It is not only automatic disconnection of supply, it is a combination of both protective equipotential bonding and automatic disconnection of supply. So in that particular case, of course, you need earth electrodes. Number two, if you go only for automatic disconnection of supply, that means without protective equipotential bonding, then the disconnection times are totally different. You have to refer to, I think, the table, there's a table in IS 3043, I think the table number 14. Disconnection time, something is written. I can tell you, one moment, please. So table, I think table 14. 1 month. So in this particular table, you can find the disconnection time, which is totally different. For example, a 230 volt for 220 volt fault, the disconnection time in case of dry condition is 0.170 second, and in case of, yes, table number 13, disconnection times for different touch voltage. So this is if you are not carrying out for the protective equipotential bonding and automatic disconnection of supply, the disconnection time, for example, a 220 volt fault in case of a dry condition is 0.17 second, and in case of wet condition is 0.035 seconds. So please make a note of this as well. Table 13 of IS 3043 2018. So we have another question from Mr. Kamlesh Kumar. Our fault loop impedance values are calculated taking into consideration the vectorial basis, taking all frequencies present in the circuit, or just sinusoidal 50 hertz. Over to you, Mr. Peter.
Okay, so here fault loop impedance, the impedance is measured by the meter. Well, I know you can select in the meter what type of network do you have. Is it 50 hertz or 60 hertz network? But well, in case of 50 hertz network, well, I know the impedance is measured. I know also that the meters are
all the frequencies are not considered. If you look at IS 732, there is a picture as well. So first the open circuit voltage is taken, or then the line to earth, for example, is shorted through a 10 ohm resistance, and the voltage drop is measured, then balance is calculated. I hope I am correct, Mr. Peter. Yeah.
Yes, yeah.
60364 part 6, there is a figure and an explanation. So it explains. So it's talking about a test which is carried out for something about 20-30 millisecond. So we cannot correlate it with the frequencies. So Mr. Nitin, when IS 3043 says RCD of 30 milliampere must be used when fault loop test failed, will it create noise and stripping and with inverter circuits? How do we handle this? Of course, if you put 30 milliampere RCD everywhere, if you cannot use electrical appliance, especially devices with leakage current, practically will be very difficult. So the idea is to make your network a TN system, either TNCS or TNS. Instead of relying more on RCD, you make the system more reliable with a TN system. I hope this answers. So from Mr. Amritlal, is there any restriction to use your meter on a highly polluted voltage where you expect different frequencies? Over to you, Mr. Peter.
Okay, well, as it comes to fault loop impedance measurement, well, you can use those meters. There aren't that many restrictions. I know we had problems in case of insulation resistance measurement, because that we make this measurement on the energized object, but in polluted areas, you get just some inducted noise voltage on the measured objects. And that was some problems, but we managed to overcome that in case of our higher models that use, for example, on a big, to test a big transformer, which could be in a noisy environment. Well, those can handle even up to 1,500 volts of noise frequency noise voltage. Of course, it's a AC voltage, but yeah, that would be the problem in case of the measurements on the energized objects.
Yeah. Okay, thank you very much. Now we have a question from Mr. Krishnendu. In Indian context, we also have a low voltage situation. How does this impact fault loop impedance? Of course, Mr. Krishnendu, voltage is an influencing factor. If you look at the formula, if the voltage is less, the impedance doesn't matter, but the fault current is less. Once when the fault current is less, of course, the disconnection time is more. So lower a big voltage drop in the circuit means the system may not work, the fuses may not trip. You have to be careful. I hope my answer is clear, Mr. Peter.
Yeah. Well, yeah, pretty much here the standard. Well, this part that we are referring here to that was on low voltage electrical installations.
No, actually, here our situation is a little bit different. In cities, for example, the voltage drop is probably within the limit. But if we go to rural areas, the DISCOM says my line to neutral and line to earth voltage, say for example, is 230 volt, but in actual we may get only 150. So in my earlier days of my career, I still remember in states like Punjab. So there are small workshops, say for example, making some working with single phase motors. What they do is instead of making line to neutral connection, they put a line, the neutral is removed and another phase, another line is connected there. So between R and Y phase, you have 230 volt and the motor works. Very dangerous way of working. So this is very typical for India, but now the situation is improving. In most of the DISCOMs, the voltages are stable now.
Okay, I'm thinking here what we would need to know is the fault current. So here, if we are far away and the voltage has dropped, we gonna select for the calculation the actual value of the measured voltage. So that would be lower, therefore the fault current will be also lower, and we need to make sure that it still would trigger our circuit breaker.
Yeah. Okay, thank you. So we have Mr. Madhav Aram has raised his hand. Mr. Madhav, if you have any questions, you can ask the question to Mr. Peter. Also, if any participants wanted to talk to us, you can raise the hand. We will unmute and you can ask the question. Mr. Madhav. Mr. Shiva Prakash.
Yeah, can you hear me?
Yes.
Yeah, it was really nice and very informative presentation about the advancement, I would say, in terms of measurements and all. One question, do you have any kind of gap analysis checklist so that we can check whether what is required and what we have, and if there is any gap, so we can make some recommendations to go for this or something like that?
Mr. Shiva Prasad, if you can introduce yourself, would be great for us and for all the participants.
Yeah, so my name is Shiv Prasad Nikam. I'm working for the company called Syngene International in Bangalore, which is a Biocon group. Basically, I'm electrical engineer, but from last 24 years, I'm into the environment, health and safety.
Okay. So, Mr. Peter, you would like to answer this question?
Okay, so well, I know that in the standard, there's the whole checklist of all different parameters that you need to check. And when we do the network verification, we perform both the visual inspection and the tests with the meters. So there's a whole big checklist of all different parameters that we need to look into. And of course, it differs depending on the system that you are testing.
Yeah, Mr. Shiva Prasad, I think your question was related to in case of any mistakes, how to identify the gap, what is required and what is not available. Am I correct?
Yes.
Actually, this is a real challenging problem in India, because this test or this information itself is new in the market, even though it was written in all the standards. What happens is there is no habit of making a circuit proper until now, because we don't have the habit of measuring these impedances. In my experience, out of 100 measurement which we are making, almost 50-60 cases, the sizing of the protective devices and conductors are not matching to the requirement of the standard. So the gap is, check your protective device rating, check your wires. Number two, loose contacts. because we only make research on the earth electrode. We never try to find out the continuity resistance of the fault return path. This is another kind of check. So it actually varies from industry to industry. We cannot make example 1, 2, 3, 4. These are the points. That is very difficult. It changes from places to place. Also for UPS, it is a different situation. For semiconductor-based devices, such as a variable frequency drive, as Mr. Peter explained. So, it's at the moment we are in a difficult situation, but for sure we will improve. Thank you very much for the question.
And do you any kind
Yeah.
of data the site to get hands-on experience or the people to know what are the advancement, what we are looking for?
Yeah, you see, in NFE, we are trying to make a scheme based on ISO 17024, a personal certification scheme. And here means the scheme will address all these issues. The person who is having a certificate from NFE will be qualified to handle all these challenges. But you have to wait for maybe probably 3, 4, 6 months, say, for example.
Okay. Thank you.
Thank you. Also to Mr. Madhav. So over to you, Mr. Madhav. If you have some question, you can ask. So I think Mr. Madhav, there is no question. Mr. Jitendra Kumar Rathore. Okay. Also, Mr. Rajan.
Hello, are you getting me, sir?
Yes, we can hear you.
Yeah. Good afternoon, sir. Myself, Jitendra Kumar Rathod. I am working as additional executive engineer in Maharashtra. A very nice presentation and very nice safety campaign done by you. First, I appreciate you and also the presenter. They have given the nice information. But actually, what we observe in Maharashtra, the accident which are occurring in the consumer premises, that is because of not installation of this ELCB, RCCB, or you can say AFD. So my question is that we are making the aware about all these protective device to the consumer. But my question is to know whether this loop impedance, what are the values available loop impedance for the device which is available in the market like AFDD, whether the same values are there or that are much lower. I want to know about that. So if you elaborate, that will be very helpful for us.
You see, the protective devices like AFDD and all, they are not based on this particular, they are for a totally different application. The AFDD, say, for example, it is for in case of disconnection, in case of a loose contact. So they work on totally different principle, not with exactly with this principle. Here we are talking, say, for example, OCPD or RCDs.
Okay, sir. Okay. And sir, actually, also I want to know that as you are doing a nice campaign about the electrical safety, but actually how we can make aware the consumer about to use these protective devices, because even though the new buildings are going on, new connections are releasing, but even people are not using the protective devices. And the government, I think the CEA regulation or the electrical inspector also, they are not making so much aware about it. So what are the ideas in your mind to motivate or to compel the consumer to install that one?
Sir, more than the consumer, first our engineering community should learn about the risk, and we should educate. All of us together should educate the consumers. It is not like, every consumer is aware of it and he will be going to buy a type A RCD or type F RCD. No, that won't help. The designer of the building, or for houses, say, for example, the electrician should be trained. Now to train millions of electricians all over the country, it's a big task. That is why we started NFE. Hundreds of people are participating in our program. Say, for example, today the registration was, I think, about 650. So we are putting efforts to make the awareness, or more and more people aware about the situation. But we also started getting support from the government, for example. As you can see, the CEA regulation has included, we put a lot of effort for it. Now the state government, say for example in Tamil Nadu, the chief electrical inspector, his office, they have made a circular or some kind of notice for their employees saying that a new regulation has come and new demands are there. So you learn about the new changes and or the new requirements and ensure that these are followed. So also, for example, in Gujarat, this is happening. In Orissa, this is happening. A lot of state governments are already in line. The electrical inspectorates, Kerala, for example. So they started enforcing this. The second line of people, those who will be informed, is the electrical contractors, then the electricians, say for example. Slowly, maybe in 3-4 years, we can find out the improvements. Thanks for the question, sir. Thank you very much.
Okay,
So,
thank you, sir. Thank you.
Thank you. Mr. Rajan Menon?
Yeah, good evening. My question is, if we are having a network having modular UPS and standby DG set along with the transformer, the source impedance is totally vary according to the source. If the transformer is 630 kVA, your modular inverter is 400 kVA, and your generator is 250 kVA, the impedance will vary. So the sizing of the conductor will be probably to match with the maximum protection device. So in such case, how do we ensure the looped impedance will be in such a way that to ensure the protection during the low source impedance, like the DG set is 250 kVA? How do we do this?
Yeah. Mr. Peter, I would like to explain our situation. You see, the situation in India is a little bit different than in Europe. For example, almost every building in India, we have a generator, a diesel generator. Hopefully, I think in Europe, this is very rare, probably. Also, in our houses, we have a device called the inverter. It's like a UPS, but very small one. And the way of wiring the inverter itself is another point of discussion. Now the challenge is the regulation has written you have to test the fault loop impedance for various sources, different sources. Say for example in the checklist part number 2 or the format number 2. One more, I will just read it out. It is not the format. For example. Yeah, the format number 2, installation of voltage level more than 250 volt up to and including 650 volt, regulation 43. So what is written is fault loop impedance at origin of installation. You should check the fault loop impedance of every circuit, fault loop impedance tested for all sources. So now, once when we start testing the fault loop impedance for smaller sources, the other kind of challenges are happening. And now, Mr. Peter, will you be able to address this?
Okay, well, pretty much I'm thinking right now, as the regulation says that we need to test it for all sources. Well, definitely the one for transformer, but in case transformer fails and we're going to use a diesel generator, okay, it might be also a good idea. Okay, I'm thinking right now about this because it's all connected with the regulations here.
I would explain my experience, of course. So once when we start testing with a lower capacity generator, then we come up with challenges. The protective devices are not tripping. The ideal situation is while designing and installing the electrical installation, you ensure that the disconnection, even with the smallest source, is done or is considered. That means you have a 1000 kVA transformer and you have a 250 kVA DG. You ensure that the devices are able to disconnect with the source 250 kVA DG. So your job is done. Probably
you are correct, Govumar sir. The problem is then you are not able to maintain the grading. That is the only solution I know. But 630 kVA a transformer serving network having a 100 kVA DG, same due to the any power failure, this 100 kVA will be injected to this. The system grading will be totally collapsed. We are not able to maintain this. That is a challenge. Your answer is 100%. I understand that is correct only, but how do we address this?
Sir, there are solutions available. Probably we have to discuss it in a bigger forum. We have to start with the design parameters and we can do it. I would like to invite Mr. Our General Secretary, Apav sir. Sir, Apav sir,
yes,
you would like
yes, sir. Good afternoon, sir. Good afternoon. Good morning to Mr. Petru Pauli. He has done a wonderful presentation. And Gopal, you also contributed a lot. But I would like to supplement for a few things, especially from Radhan Menon and Jitendra. Radhan Menon raised one question, how to coordinate generator, transformers, or VPS, etc. There is a provision IEC 61200 TS standard. You provide the short circuit level to the lowest fault generating device. If it is VPS, you provide it at the final circuit. If it is DC, at the changeover circuit, you provide the outgoing circuit. So these are all, generically, it's available. You can do it. We can discuss at a later stage, as Mr. Gopal told. Another thing, what Mr. Jitendra, I think is from DISCOM, the thing is, the earth fault loop impedance test itself is reaching the source. So we can't blame the consumer alone. They are providing RCDs, MCBs. They have done a wonderful thing. They have provided all the coordination. Let us assume they have provided all the coordination and the safety procedures. Suppose if there is a flaw in the supplier system, and what will happen to earth fault loop impedance? We are preventing TNS, TNC in the supplier. Ultimately, the total earth fault loop impedance, which will reach the source, will be hampered by the poor non-compliance. In most of the distribution, we are seeing non-compliance of PME system. One more thing, because of this non-compliance, your poor earthing system, the temporary over voltage is likely to be imposed on the consumers. Because there are a lot of issues. It's a joint and collaborative approach, and stakeholders are different, not only the consumer. That's why NFE is providing as a awareness and certification scheme for the designer, installer, and verifier. So this is my point, Mr. Gopa. I hope if the supplier has, of course, supplier has every right to disconnect or to refuse supply. It is in the regulation. Now the regulation is very clear. They do not insist a specific technology. They insist only a what do you call a safety margin. They provide you whatever, whether you provide FDD, RCD, TT, or TNS. Your system should disconnect the supply without causing danger to the person and equipment. This is very clear. So we have to, how to achieve it? We have to deal with the correct selection of devices and correct approach. That's not a single thing, simple thing. It depends upon the various type of instances, Mr. Gopal. So these are all my opinions. Thank you, Mr. Gopal. Over.
Thank you very much, sir. Thank you very much. Thanks to Mr. Peter. We are, as I said, as we discussed at the beginning, we tried to close with 1 hour 30 minutes. So as usual, it goes to 2 hours. We have reached 1 o'clock in 2 hours. So thank you very much, Mr. Peter. Over to you, Mr. Dominic. I hope you are there.
Yes.
Yes.
I think I was just a little worried because the cloud, the recording is going up. So when we want to reproduce this as a to share, so the size will be 3 GB. So sharing will be an issue. So anyway, I think we have taken exactly 2 hours now, 1 p.m. Great to have you all. As I said in the beginning, we are going to have a series of 9 city Tier 2 city program with Bureau of Indian Standards, the initiative Bureau of Indian Standard. With NFE, we are going around, and we'll be sharing that information to all the participants. We're looking for good sponsors because every program costs a good amount of money to us, and this is a non-profit organization. NFE is a non-profit organization, So every penny that is collected is going back to the society in way of book, the best practices book which we need to print and circulate. So any amount that we come through the sponsorship for program is very much appreciated. So I would urge the participant here and all those manufacturers also to come forward, generously support us. So we look forward for next series of webinar. We'll shortly will announce that, and we have, as I said, we have almost covered good, maybe over with CAPE and NF, we covered more than 19,000 audience. 19,000 people have been participating in various platforms. So I look forward. Thank you, Peter, to joining from Poland. I know it's you crossed the breakfast time. We are holding you, and we are ready to go for a lunch. And I'm sure my audience also are hungry to go. And this is a weekend and a long weekend. We have holiday on Monday and Tuesday, so people are waiting to. I think the family must be insisting them to close this webinar so that we can pack and go. So thank you very much. We wish you a happy Dasara. On behalf of NFE, wish you all safe, Dasara. Look forward to see you again. Thank you.
One
Bye-bye.
subject, one more point. Our next webinar is also about fault loop impedance. But this time we will concentrate on a new standard which is published in India, which is very critical in every building. Every building we use lift and escalators nowadays in the multi-storied building. So our next webinar is about again fault loop impedance, but how this is written, how it has to be read, and how it has to be implemented in multi-storied buildings. Thank you very much. Thanks. Thank you very much, Mr. Piotr and Mr. Dominic. Over to you, Mr. Dominic.
Thank you, sir. God bless you all. Bye-bye.